Hello everyone. Today we are going to solve two example problems, and one of them, if we were in class, I would do this first and then I would ask you to do the second part yourself. Okay, so we're gonna try to do the same thing. So I'm gonna solve part one, this one, and after I do this, please don't look at the solution for the second one, and try to do it your own, and then look at the solutions. And the solutions will be provided on PDF form and also in the video form. And you can also access to these files on the Fridays page on Canvas. You'll find the links to look at these, okay? So the problem is very similar to what we've done in chapter 5, but again, remember this is chapter 6, so there's friction. Although we are going to ignore drag force in this case. It's more like friction. There are two masses. The inclined surface is frictional. Coefficient of frictions are given, static and kinetic. Angle is given, and the masses of the two objects are given. First thing to do is to draw free body diagrams for each block. If we were in class, we would ask you to get them checked, but of course we are not able to do that. So we're focusing on M1 first. M1, I'm gonna draw it like this. The forces acting on it is the weight force going down. Let's call it W1. There's normal force. Although there are no other normal forces, I'm just gonna label it N1. And there's tension, it's a pull force, so it's going that way. There's also friction, so I'm gonna put a note on the side, but I don't know which way it is because friction opposes to the intended motion, and I don't know. They didn't say if the system is moving or not at all, so I cannot assume something. So I will need to figure that out. Okay, so which way if there's any, which way the motion is, and then the friction is going to oppose to that. So there are no other forces except friction. Since the motion is along the inclined surface, so I would probably choose x direction horizontal to the surface, for no reason really, because I'm not sure which way is x motion. So I'm just gonna say to the right is x, upward is y for this free body diagram. For the second one, for M2, so we have the object hanging. So there's tension force upward, same tension because it's the same rope and the pulley is ideal, so I don't need to label them differently. And weight force is going down, and there are no other forces acting on M2. To make the rope line the same direction, since I already said for M1 it is up the incline, if I follow that line over the pulley and going down, so I'm really saying that going down is X for M2. Again, this is something I choose to do to be consistent, and it will make my solution easier this way. Okay, so when you have friction, it's really better to think about the system to figure things out, like as they're asking now, determine the direction of acceleration. We don't even know the direction of acceleration. We don't even know if it is moving or not. So we cannot make wrong assumptions here. Okay, it's very dangerous to do so. Let's find out then. Okay, so we need to figure out the direction of the acceleration. Later, they're gonna also ask us to find the magnitude. So we need to find out the forces along the rope line. So I'm just gonna highlight that direction. Oh, this is too bright. So if I draw it like on this M1, this is the rope direction. So I'm gonna put an arrow because I'm choosing that to be the X, right? Although I'm showing that, I just wanna kind of remind you, as a system, this is how the rope is going. So along the kind of positive X direction. All the forces acting on the X is what matters. So the tension is one of them, but as you can see on M1 is positive tension, on M2 it's negative tension compared to my positive X choice. So tension is an internal force. And that's why in here we said that, kind of give you hints. We gave you a hint and said ignore internal forces. So tension is not the determining thing to figure out the acceleration. I'm going to resolve W1 into components first. This is W1y. Okay, and so let's think about all the forces acting on X. Okay, so for M1 we have Wx this way, and this W1x. For M2 we have only downward force W2. Again, I'm ignoring the tension forces because they're internal. There's also friction, right, on M1, but I don't know which way it is. So again, I'm still keeping in mind there's friction, but I'm not putting it in anywhere. What I need to do is, so this is like, think about what we did with the without friction problems. This is like the two ends of the rope, and I just want to figure out which way pulls it at a greater force, right? So then if there was no friction, that way would be the direction of the motion and maybe also acceleration. So let's find out what those are. So what is W1x? W1x is W1 times, if you look at the free body diagram, this is your theta here, right? The tilted surface. So it is really sine theta here. So W1 is M1G. That's the definition of the weight force, sine theta. If we plug the numbers in now, M1 is 5 kilograms. It's really ugly. 5 kilograms. G is 9.81 meters per second square, and sine is 30 degrees. And from this I got 24.53, not 63, 53 newtons. Okay, so and W2, let's just find that out as well, is simply M2G, right? And M2 is 5.5 kilograms times 9.81 meters per second square, and that gives us 53.96 newtons. So it looks like W2 is much bigger than W1x, but again, it still doesn't necessarily mean W2 is the direction of the motion, because we have friction. So what I'm now thinking is like, okay, the system is being pulled this way, maybe. If that's the case, the friction will be opposing to that, right? So on M1, there will be friction this way. So I need to check if that the difference between W1x and W2 is much large. I mean, is it larger than the maximum static friction? So is it going to be able to move the system or not? Okay, so one thing I'm doing here then is to find out the difference between W2 and W1x. Let's just write that down first, and that is 29.43 newtons if you take the difference of these two values. Okay, that's what you get. On the other side, I'm trying to find if this amount is more than the maximum static friction, because if it is not, that means we can still build up and it's still not moving, right? So let's just find out this maximum static friction. That will be the only time that we use the equation, right? And since static friction is on object 1, then I'm going to use mu as n1. And what is n1? To find that out, we need to go back to the free body diagram and see the y-axis. So I'm going to write the second law for y component for m1. And do we know what the acceleration along y direction is? 0, right? It's not even moving. So sum of Fy becomes n1. Let me just change change this quick. N1 minus W1y equals to 0. So the normal force, it would be M1G, which is W1, and y component it takes cosine function, cosine theta. And if you plug the numbers in from here, you get, let's see, 40. Oh, I don't have the number for this. 42.47 newtons. Okay. So that means if I plug this back into N1, I will get maximum static friction. Let's do that. Mu S is 0.7 times 42.47 newtons for the normal force, and that gives us 29.73 newtons. Very close to the difference, right? So if you compare, what you see is this, the difference between W2 and W1x is less than the static maximum friction. What does that mean? That means we don't have enough force. It's not on the verge of moving yet, right? We're still building up, so we need a little bit more. Maybe if this M2, instead of 5.5 kilograms, if it was a little bit more, not even like more than half a kilogram, if it was a couple more hundreds of grams, then we could have more force of W2, and then the difference would be bigger than Fs max, and then the system would be in motion. But this tells you it's not even moving. You don't have enough force. You don't even bring the system to on the verge of moving. Okay. So the direction, there's no direction because not moving, and the magnitude is simply 0. Okay, so don't assume that the object has to accelerate or moving, because like in this case W2 is bigger, so it's going to move that direction. It doesn't, it's not necessarily, it depends on so many things, and you have to check first. If the problem is not clear, if it's moving or not, you have to verify first, okay? And that's kind of what we did here. So now you can do the part 2 of the problem. Hopefully this helps.